Thank you very much. It's a pleasure to be here after a few years of hiccups in traveling, especially from the other end of the world. This is joint work with Paul Escapil, who's now doing his postdoc, and it's about maybe a different perspective on how to deal with Helmholtz scattering, as the previous speaker was talking. And just to set up the framework for this, and before going into the notation and so on, this is a small perturbation, random perturbation talk. So yesterday there was a distinction between intrusive and non-intrusive methods. This will be about a somewhat non-intrusive, but a method that only works for small perturbations. So small random perturbations will be our basically our purpose, and the applications of this, of course, are more on the industrial use or wearing of electromagnetics or acoustics objects and so on. And we will deal with the family of scattering by sound soft, sound hard, and transmission problems in the same setting, but I won't be specifying each particular case because then we would spend way too long. So what I'll say here is valid for 2D, 3D. I don't know if there's a pointer here. There you go. Okay, thank you. So we have an unbounded domain wherein we have a bounded object of Lipschitz domain initially, then we will restrict the or make the object a little bit smoother. But then I'll end up my talk by saying that some of the things we're doing, maybe we cannot prove them on Lipschitz domain, but turns out that the numerics seem to be quite good after all. So we have our bounded domain D, an exterior domain or complement DC. We have the boundary gamma, and then we have, well, Dirichlet trace, the Neumann trace, and we call this L kappa our Helmholtz operator. And we have this generic problem where we're looking for the solution of the homogeneous problem here with some boundary condition that will depend on the different cases, where U is the scatter plus the incoming wave, with the incoming wave in this case for simplicity, assuming that is satisfies the homogeneous equation. And of course you need to, because the domain is unbounded, you need to include some Sommerfeld radiation condition here. And so as I said, so we have the sound soft, sound hard. We have also the impedance problem and the transmission one, where you would also like to see the solution here. And we will perturb the boundary gamma in a certain way. And this D here it can be, so in this sort of generic framework, we have this beta 0, 1, 2, 3, and then you have your generic domain where it's basically the exterior domain, except when you're talking about the transmission problem. So how we want to model this? So the motivation, as I said, is small perturbations. We do need to have some smooth nominal domain. Maybe the perturbation or the realization of the domain you're having has some occurrence of a less regular, but we're still in the small perturbations regime. And the solution Ux of now of omega, so the realization of our probability space for a domain is the solution for this P beta, so any of this family of problems. And we will use a tensorization of this problem. So as you can expect, we will deal with some of the curves of the dimensionality that were discussed yesterday, and certainly the previous weeks during this program. So what do we want to estimate? We want to estimate the obviously the expected field given by this uncertain shape, and then some expectation on the covariance or variance or pseudo variance, since we're dealing with complex fields, but I won't be specifying the variance of the pseudo variance depending on the complexity, but the same program works for that. So now, how do we do this? And here we follow the steps by Harberg, Schneider, Schwab. Also, this work from Peterson, Schwab, and then it's been carrying on for the last 10, 12 years now, 14, 15 years maybe. So what is the idea? So of course, you want to obtain the problem in this unbounded domain, and if we try to do some finite element discretization, that leads to something ridiculous because it's an unbounded domain. So we will reduce this to the boundary using boundary integral equations, using the integral representation of the field. And so first we need to understand how do we model this shape variations in the scatterer. So first we will have a parameterized pullback T of T, where this T, small t, will be basically the size of a perturbation we're doing. And then we will see that this size of a perturbation is relative somehow to the wavelength. So here we'll just talk about T, but then when we see the numerics, we will clearly see that this T has to do with the wave number or the wavelength that we're dealing with. Okay, so we have this, so we have a nominal domain D, and then we have this mapping onto this realization omega, where we need to have a one-to-one bijective, and that this is smooth enough to perform differential calculus, because the other element that we will be using are the shape derivatives of the solutions. And the idea is, in fact, is to do a first order approximation using the shape derivative. That means linearizing the solution for each realization and transfer. And by doing so, what you do is you transfer the stochasticity onto the right-hand side of the boundary integral equation. So you do a first order approximation, and then what you end up having is a deterministic volume problem with a stochastic right-hand side. And so when you do the boundary reduction, everything is left on the right-hand side of the equation. So, of course, you want to solve this numerically, and you will end up with a tensorized boundary integral equation once you take the statistical moments. And this is something you want to avoid, of course, especially if the object is very, very large. And so the way to deal with it is using this so-called sparse approximation and the combination technique by Harberg, Peters, and Silber and Morgan, where you get a system that is reduced, especially when you look for large numbers of n. And then we will also discuss, I give you some ideas on the preconditioning side. So in a nutshell, this is sort of the scheme of the method. So you have, we're dealing with Helmholtz UQ. So you have the moments of the volume quantity. You do a first order analysis where you will end up with the shape derivatives. Then you do a boundary reduction of this problem so that you end up solving boundary integral equations. You solve them numerically, and you want to avoid dealing with the curse of dimensionality. And so you use this combination technique, and then you reconstruct the solution from the boundary unknowns that you found into using the integral representation, so that this is the whole scheme. Okay, so let's now start putting more details into this. So now D will not just be Lipschitz, we will want it to be C11 with its boundary gamma. We have a probability space, and we will consider not any transformation, but transformations given by this vector B that's in the Bochner space LK from the probability space into W1 infinity, such that we assume that this nominal domain is perturbed and the perturbations in the expectation of this field is a zero. Otherwise, you change the domain so that you achieve this condition here. Then you introduce this mapping that will shift the boundary from X to from the boundary on the nominal boundary to this perturbation on a parameter T. And then you can show that there is an epsilon larger than 0 for which, for every t in this, or let's say for each, and maybe I should draw this, we have here. So any perturbation in this area here, or this cylinder around your, or this tube around your boundary, generates a bi-Lipschitz diffeomorphism. Okay, and then you abuse a little bit the notation, and then you extend this same transformation into the domain. The bounded objects are still bounded Lipschitz domain, now almost everywhere in the probability space. And then now you conduct your first order analysis. Now, provided that your t is within this tube of epsilon, so smaller than epsilon, then we seek our expectations and variances for this problem. And you know that for each t in this realm, you get the expectation of a field is going to be, let's say, the nominal field, so the field solved on the nominal domain, plus something of error t square, almost everywhere, for each compact within the unbounded domain. In this case, we're talking about, so this could be DC, or it could be on the, if it's in the transmission problem, you need to add the interior domain. Then the moments will be of order tk, with here an appearance of the shape derivative, and a second term of order tk plus 1, and the shape derivative is defined in this way, that is valid within this domain. Okay? So we need to somehow evaluate u, which is fairly easy. You have your boundary element code. You just do it on one mesh, and then you calculate this statistical moment of your shape derivative. So in its general form, you know that the shape, or the shape derivative, is a solution of the boundary value problem, where you have an appearance of, again, so the shape derivative solves the Helmholtz homogeneous problem, but the boundary condition changes. And this is a little bit the gist and the idea of doing this linearization, is that you basically push the stochasticity on the right-hand side. This is your boundary value problem. So for instance, in the case of the Dirichlet condition, now you have that the shape derivative for the Dirichlet problem, again, solves the whole Helmholtz equation, homogeneous Helmholtz equation. But now your right-hand side for the shape derivative, this prime denotes the shape derivative, now has this term here, where you have the Neumann derivative of the nominal solution onto the nominal boundary, and you have the appearance of the perturbation vector V. So good news, this we can transform into a boundary integral equation, and you just impose this condition here. And now you will have these random boundary integral equations, or random on the right-hand side boundary integral equations, and then you will tensorize this when you want to obtain the moments for this for the perturbation. So boundary reduction, well, I won't but just quickly go through that. Then you have all the Fredholm theory. You can show well post in this. And if you look at the deterministic BIEs, so boundary integral equations, so we have, of course, will be in either H1 lock or H1 0. Also on the for the Dirichlet case, and then of course if it's unbounded, we need to localize it. Then for separable spaces X, Y, and F, B now denoting the general form of the boundary operator applied on the right-hand side for the shape derivative, let's say trace, but it's not the shape derivative trace. This is a strange object, and this is, you have to be careful on this. So this is some psi prime that is not necessarily related to the object that you want to find. So it doesn't necessarily mean that it has a physical meaning. So it's just a quantity that will allow you to reconstruct the solution. Now, when you randomize this, now you look this in the, and I'm using notation, randomize is not the right equation, but now you include the fact that this G here is going to have a special form that brings in the stochasticity. Then you look for Xi, again, for the deterministic problem, then you have a Xi prime that now belongs into this space, and you need to solve for this problem. Yep. So, because you need to do this statistical moments, you are tensorizing the BIEs, and this is what you obtain. So now you have the previous version of the boundary integral equation. Now you are solving again for the same boundary integral equation on the nominal domain once, and then you need to tensorize this on the gamma k, so parenthesis k, which means now the boundary has been tensorized k times. You have here your tensorization of the boundary operator applying to the the kth to the kth moment of G, and then you have a tensorization of the Z, which would be either the weakly singular, the hypersingular, or some boundary integral operator, depending on the problem or the formulation you choose to solve the problem. You have the kth moment system with stochastic right-hand side. So now let's put this sort of framework into a concrete case. So now you have the soft case. For instance, you can so you have the single double layer potentials, denoted by a single layer, double layer, and this R kappa is just the vector potential where you have the double layer and the single layer. You have V and K being the single and double layer boundary integral operators. And for the sound soft case, you have G0 equals, this should be the sentence. No, this is correct. Sound. You have the Neumann trace of U times V, which is your perturbation, normal into the normal direction of your nominal domain. Now, if kappa is not a resonance of the Dirichlet problem in the interior domain, you have a right-hand side given by the Dirichlet trace of your exterior domain. So this is just the sound soft problem. No, sound hard, sorry. U is the full, this should be sound hard. And then you have G0 here, then you have, this is a tensorization on the H1/2 gamma space, K equals from 2 onwards. And we seek for the H-1, so the Neumann trace of U in H-1/2. And we're looking for this quantity here that will be reduced to a single name. So this is the statistical moment of 1/2 of the Neumann trace of the shape derivative in H-1/2 tensorized. So it's a bit complicated, but this is just your previous B. This is your F. This is your Z. This is Z tensorized, and this is the Neumann, and this is now basically your neuron. And then you can reconstruct the field U from obviously the integral representation formula. You have the incoming wave times now the plus or minus the single layer of the Neumann trace in the exterior domain. And then for the moment you have U single and double layer and single layer of this quantity here in once you obtain this object here. So how do we discretize this? Well, we use a Galerkin method, and as I said, this is one version how you could solve this. You could also choose a different version for this, but you have to be careful on how everything traces back so that you can reconstruct the full field. And then we'll apply this combination technique. So Of course, we want to have some idea on convergence and so on. And for that, we also assume that there is some smoothness in the solution. Otherwise, we cannot say much. We will also need that for discretization into a sequence of nested spaces. And so the idea of tensorized approximation means somehow that you will play a little bit between a coarse approximation and a more refined on certain elements, and then choose a proper combination of this. We use low order BEM, and here is theoretically, then I show the numerical results for this. And in the case of Helmholtz, you can prove that you have a discrete in sup condition and quasi-optimality in X. Of course, for the not only for the deterministic problem, for the boundary unknown, but also then for the tensorized version of it. Maxwell, it's a bit different business, but it all has also been done. So what are we looking for? So this is the Galerkin formulation for now the discretized L denoting the largest or one of the nested of the nested spaces XL in X. So it's a conforming discretization in H minus 1/2, H 1/2. You choose depending on the specific problem you're solving, and then you have the right hand side. And then you can show that if the solution is sufficiently smooth, then you will get a convergence rate of H to the S for S, the smaller P plus 1, where P is the degree of approximation. Of course, I should have put it here. So, but we're talking about basically zero order, first order. We're not going further than that, but this is the standard bound. Now for the tensorized Galerkin formulation, you get a similar thing, but now the objects are in this tensorized space. So you're working on gamma kappa, and you're tensorized. You could tensorize your mesh. You have your mesh, and you can think of a tensorization of it. And this is the full Galerkin. You're approximating it in a similar way with the same elements and so on, and you get a convergence rate of the similar type. Okay. Now, the idea, of course, is not to use the same amount of degrees of freedom for the tensorized problem, because basically you end up with the issue of the dimensionality. But since it's a coercive problem, you still need to resolve a minimum wavelength or a minimum discretization level, so that after that you can start converging, similar to what Francesca was showing in a while. So there's this minimum resolution level L0, and after that instead of using an n to the k system, you end up with n log k minus 1 divided by 2n. And the idea of the combination technique is that you solve independent subsystems, and then you recombine this into a proper solution. That's a result by from President Schwab, where if you do the sparse tensor approximation of these problems, then this sigma hat here being the sparse tensor approximation with respect to the original function, then you get an error. And of course, the same smoothness as before, that now is an HS of log of H k minus 1 divided by 2. Okay, so of course, this is a smaller factor into the convergence, but it certainly helps on the numeric side. Now, how do we solve this numerically? So what we'll do is we show 3D, 3D full Helmholtz using BEM++. We have an incident wave for k equals 2, but the k will be changing for, so k, not kappa, k is the tensorization level, so the covariance and so on. Kappa is the wave number. So this run into a Linux server, so you don't need to have a supercomputer for anything like that, but you still need some computing power if you want to do this nicely. P1 functions or P0 functions, depending on the case. And we use hierarchical matrix compression. There is a discussion that it seems in this version of the slides I skipped. I apologize for that, but the issue of preconditioning, shows up, and I'll mention this later on. In fact, here, so not only you're doing hierarchical matrix compression, which also helps on the speed of on the numerical side, but also using an iterative solver. And there is a plugin you can download here for you to use. So we will compute two things. One's called the far field. So the far field of this is standard in people do wave scattering. Is basically this expression as to what you see after all the evanescent phenomena go away, or the least energy prevailing. And then another measure of merit they usually people look at is what's called the radar cross section on the unit circle, which is measuring decimals. Okay, so here we start with this cage shape object perturb according to this perturbation. So the V is given in this way. So you have this cage shape and then Cartesian coordinates, and then you have this mesh, and then for different T's, you see how things getting deformed. So of course, this is a big deformation, T equals 1. This is really something different. T 0.5, it already looks different, 0.25, 1. So, and you will see that there is a dependence on kappa. So let's look at two wave numbers, kappa 1 and kappa 8 equals 8 with 20 points per wavelength. That gives basically meshes of 3,000 and 9,000 elements on the surface. Remember, we're doing a boundary integral problem. This here is the radar cross section of UT solved on the actual perturbated mesh. So we will compare solutions computed on this specific meshes and their their approximations by either the nominal solution, so the solution on the kite-shaped object, and its correction by a first order correction using this T times the shape derivative. Okay, so here the axis is T. So this is how T, so T, of course, if T is 0, when you measure the error between the actual solution and the nominal solution, if T is equal to 0, of course, it's 0, because when T is equal to 0, you have your original problem. Same thing for this other approximation in blue. But for kappa equals 1, then you see that there's this what you would expect. So you have a sort of a parabola here for kappa equal 1. So obviously the nominal domain is a bad approximation for T over 0.25, 0.5. Now this is for the sound soft, this is for the sound hard, similar situation, and now you see that the picture's pretty much the same. But when you move into frequency, to a higher frequency, then it's interesting what happens. Basically what you see here is condensed into this little regime here, because T small is actually dependent on what kappa or what the wavelength is. So here you have a much smaller wavelength. So basically what you see is that if you do your nominal domain approximation, you just say, okay, I had the nominal domain, I have a larger wavelength, and I approximate the solution as if I had been on the nominal domain, then of course, it's only worse after a certain point, and after this, it doesn't change much. But of course, if you use this approximation and you carry on now pushing T to a higher value, then basically you're just simulating something completely different. So this is just to show how that the concept of T being smaller than epsilon is actually a wavelength dependent parameter. Same thing for the sound hard. Now,
Carlos,
sorry. Yes.
So the scaling is 1 on kappa, yeah, roughly speaking. Because you go from 1 to 8, and then this, the middle one is about 0.125, I think, if I read your.
Exactly.
I cannot read it completely.
So this is the scaling you should look at. Epsilon times kappa.
Yeah.
Not quite, because it depends on how close you're to a resonance. The epsilon range.
This is the exterior problem with the Sommerfeld. There's no resonance.
Of course,
There can be near resonances, so then you have resonance poles close to the.
Yeah, we're assuming we have no. So we are outside the pole the resonances of the problem. So you say, for instance, for the house on heart, you are in your kappa should not be in the interior resonance of the Laplacian.
I mean, you can have physical resonances.
Yes.
Also for exterior scattering problems, physical resonances in the complex plane.
Yes.
When you're close to such a pole, then of course this will severely limit the range of epsilon.
Yeah, this is
so the epsilon should be multiplied, say, with the condition number of the problem. I think this is the right measure.
That well.
Let kappa stand for the condition number.
No, but
yeah,
for the condition number.
Yes, because I think this is the right quantity to compare.
Yeah, but so that's a different. So I'm not in this scenario here. I'm just trying to say that epsilon. So what this shows is that your t smaller than epsilon is epsilon times kappa. So if kappa is large, then
no, epsilon over kappa.
Epsilon over kappa. Yes.
But this is true only for nice, so benign situations, when you don't have quasi-resonances close to the real axis. When you have quasi-resonances, then it can be even exponential in kappa, epsilon over e to the kappa. And it's very bad.
Well, yeah.
But these are isolated points, and in your experiments, you were probably at a safe distance from these dangerous frequencies.
This is correct. This is correct.
Nominal problem does not have a resonance.
So here the nominal problem was on this.
Yeah.
Here. Of course, I think we're talking about this pattern.
We're talking about quasi-resonances. These are poles of the resolvent very close to the real axis. And they determine the condition number. This is why it's better to replace kappa with, say, the condition number of the scattering problem. And this will limit the range of or the validity of your linearization.
And this you can also deduce from a perturbation analysis. So if without much more, let's say, as a physicist would do, just take your epsilon and then t, and then you look what this is. So the point being that it's not an absolute value once you do this. And I agree with you, this could happen. Now, of course, you want to have a nominal shape with you. Or you start with a nominal shape where you know what the resonance is, and then you move away from it. Maybe that's the solution. That's a trickier problem.
Well, there's no real solution to this phenomenon because it's built into the scattering problem. It's physics.
Yeah.
So this you have to put up with this kind of impact of quasi-resonances.
So, okay, so then if you look at this, the same plot here, but now in log. So this is T, I apologize for this, it's T1 and T2. So you see you retrieve what you expected on the error side. So T square, an error of T square for the first order approximation, which is the blue curve, and basically order 1 for the first one. And then here is this is what happens when what I was mentioning before about the relative value of T with respect to the wave number. Now, let's consider, for instance, the transmission problem for now, let's say, just for the sake of simplicity without any jumps on the mu0, mu1. So you have a, let's call it low frequency case where you have a K0 of 0.4 and a K1 equals to 1 and a kappa 0, kappa 0, kappa 1, kappa 0, kappa 1, 2 of 8. And for this, you know the Mi series solutions, you can compare your solutions to this. Here we use a single trace formulation. And so it's called the multi-trace, but basically it's a single trace. So, well, it's not a single trace, it's multi-trace because you're basically saying, see this vector psi here, psi 1, psi 0, oh, sorry, psi 0, psi 1. And you plug that in. This is the incoming, so the trace of the Dirichlet and Neumann values at the boundary. And then you have this tensorized here. Of course, if your transmission problem, you have traces from above, traces from below, then you're tensorizing that. And then here you see 1 over h, you see the convergence. This is for the full space. So this is full space convergence. We're not doing any sparse combination technique or anything. So you have 0.1, this is the low frequency, you have the high frequency. In this first row are the solutions on the nominal domain for the boundary unknown of, so this is the boundary unknown in h1, h minus 1/2. So Dirichlet Neumann traces of the solution. Now you do this here for the low frequency, looks very nice. Then of course for the high frequency, then it gets basically the same. But now the interesting thing happens here. So this is the 1 over h. So you have a convergence rate for h being the discretization, the spatial discretization that you're fully tensorizing. In this h1/2, h1/2, h minus 1, h minus 1/2 gamma times gamma. So you have these tensor spaces now. And you compute the error and you see, well, of course, things converge. But when you look at what happens so I'll look here. When you look at the degrees of freedom, then the issue is that you will see that the degrees of freedom here are obviously tensorized. So this is an n square. So you have, if this h represents n degrees of freedom, now you're here using n squared degrees of freedom. Now here you're using sparse for approximation. Here, of course, for high frequency, this is the Dirichlet trace, this is the Neumann trace. You get the convergence in h, and then for different L0s here, you start converging faster and faster as you include a how you call that, a better sparsification of your elements. So L0 means basically I never did the sparsification, you use this whole thing, then I start using different levels, and then what you see is that the levels start going down and you converge as the theory should show. Now on degrees of freedom, then you have a difference of order 2 degrees of freedom in the case of high frequency, also for the case of low frequency, and for Dirichlet Neumann traces. So this is a relative error in the energy norm for Dirichlet Neumann traces for these tensorized. Now, one thing that unfortunately I skipped is that when you're solving these problems and these are full matrices using an iterative solver, you may want to precondition. And the way to precondition this, you can have several strategies. If you use Calderon preconditioning, you cannot expect that the Calderon preconditioner will do exactly as you want on the non-tensorized way, because the preconditioner basically doesn't apply everywhere. So you won't end up with a compact or identity plus compact. But what we saw numerically is that it does help a lot, and without preconditioning, you still need it will still take a lot of iterative counts, iteration counts to get it done. The other thing we saw is that if you had, we did this, unfortunately, I can show you this afterwards for those who are interested. If you do the Fisher cube and you have one of the faces, for instance, with some perturbation, of course, you don't change the edges of the Fisher cube, but you have perturbations on piecewise, let's say, on each face. Then you still get some really good approximation by using this approach. So of course, and you have to limit the places where your perturbations can be allowed, but numerically this shows well. And then the other thing we did is that we applied this to gratings. So for instance, you have, and this is very common in optics and also astronomy, where you have some sort of grating, and then the actual manufacturing has some errors and so on, and you want to measure this. This is highly sensitive, and this also, this approach also works same basically methodology or same procedure. So so this was published a few years ago now. So there are a few ideas on how to maneuver the combination technique with the iterative solvers and the preconditioning. As I said, you need to use some preconditioning in any case. So the theoretical results for Maxwell are already available, and there is a work by Jürgen Goltz also on how to do this. Now the interesting thing is now you can apply all the machinery on now this fast Calderon or compressed or biparametric operator preconditioning onto this, so that this can go much faster as well. And then, of course, you would like to see several right-hand sides at the same time. So, as I said, well, there's this layered structures and period structures extension. So, I'm here. Thank you very much.